Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tear. And as I do every Saturday, I'm featuring another biography of a famous mathematician. These are all listed chronologically at the end of volume 2. That's the green volume in the middle here of the Math Lover's book. And I'm up to the 29th out of 80. And that one is Thomas Bayes. He lived from 1701 to 1761. I guess we're starting out in the 18th century now. Yeah, Thomas Bayes was an English mathematician, and he's most well known for one result he came up with, and that's this formula in the middle of this page. This is known as Bayes' theorem. This is the simplest version of Bayes' theorem. It's just a very simple law in what's called conditional probability. Here's a larger picture of this formula. It's actually very easy to derive once you start learning probability theory. I'm not going to go over this formula on how to derive it, but when you start studying statistics, this is one of the first things you learn. And I think I should explain at least what this notation means. So A and B are events. So, for instance, we could be talking about probability of rain. Say A is what's the probability that it'll rain tomorrow, given that it's rained today. Say B is the probability that it rained today, and A is the probability that it will rain tomorrow. Well, to get that, you would compute the probability that it rained today, given that it rained tomorrow, times the probability that it's going to rain tomorrow, divided by the probability it's going to rain today. Something like that. Maybe that's not the best example, but it works. And you could do it for other things too. And this is the simplest form. Like I said, this is the simplest form of Bayes' theorem. This is the more general form. In general, you can expand B into a sum of components. So, for instance, if B is the probability that it rains, say the probability it's going to rain next month, given the probability that it rain this month. Well, BJ could be the probability it rains on any particular day of the month. So, say B1 would be the probability it rains on November 1st. B2 would be the probability it rains on November 2nd, all the way down to B30, which is the probability it rains on November 30th. So you could do that. And, you can apply this formula to calculate these probabilities. And, it's not very hard to derive this form of Bayes' theorem either. I think I should say one more thing about Bayes' theorem. Even though it's very easy to derive and it's easy to generalize, it's pretty counterintuitive when you apply it. Sometimes it gives you very counterintuitive results. And I can give you an example. I'm not going to go over all the math in this example, but suppose you have a drug or a medicine that is 99% effective, like a vaccine. You suppose you have a vaccine that's 99% effective in curing a particular disease. If you have no, actually, not a vaccine. I'm sorry. Suppose you have a test for a disease like COVID-19. That's a good example because it's the most recent pandemic, and I believe there still is COVID-19 going around. So you suppose usually you might want to get tested to see if you have it, or you're going to get it. And say your test is 99% effective. That's pretty good. I think most tests are at most about 99% effective. And there's two ways you can say how it's effective. It gives you a false positive or a false negative. So I'm saying 1% chance of false negative or false positive. That means that if you have COVID-19, there's 99% chance it'll tell you do. And if, there's 1% chance it tells you the wrong thing, that you don't have it. And vice versa. If you don't have it, there's a 99% chance it'll tell you you're negative, but there's a 1% chance you'll get a false positive. So that's the scenario. And now further, let's suppose that we live in a community where only 1 in 1,000 people are affected by it. Right now, that's probably the case, or close to it. It's not really prevalent right now. I mean, in 2020, it was much, much more prevalent, but right now, it's a very small risk. So suppose you test everybody in a community of 1,000 people to see whether or not they have COVID-19, and say you test positive. Then what would you think is the probability you have COVID-19? Well, it's a 99% reliable test. You might think that's really reliable. I probably have it, right? Well, guess what? There's only a 9% chance you have it. And why is it so low? I mean, if we said this test is so reliable, 99% reliable, well, the reason is because it's very unlikely you live in a community where only 100,000 people have it. So you're very unlikely to have it. You're much more likely to get a false positive than you are to actually have it, just because it's so rare to begin with. That's what people don't realize, when you do things like this. So statistics can be very counterintuitive. As a matter of fact, I think there's a book called Lies, Damn Lies, Liars, Damn Liars, and Statisticians. It's very easy to lie with statistics. And I think companies do this all the time because they want to make their products look a lot better than they really are. Just thought I'd mention that. And there's other motives for lying with statistics. It's hard in general to lie with math because numbers don't lie and logic doesn't lie. But statistics can be misleading. You can be misled. You can be deceived by statistics more than any other type of math that I know of. Just thought I'd mention that. But on the positive side, Bayes' theorem is very, very useful, and Bayes was a really important mathematician because of his theorem. I think also some other results he came up with. And another thing he did was he defended. He lived in the early 18th century when just shortly after Isaac Newton came up with calculus, and Gottfried Leibniz, who was German, came up with his own version of calculus, which nowadays most people consider was superior to Newton's. And I think for that reason, I think Newton got a lot more criticism from his calculus than Leibniz did. But a lot of people didn't like calculus when it first came out. It said you're dealing with infinitesimal quantities or infinite quantities. How can you generalize something to infinity? And that's probably the hardest thing about calculus. But I guess what Bayes did was he went through all the analysis and he showed first for himself that Newton's calculus was completely arithmetically, mathematically sound, and he defended it against a lot of his critics of the day. So maybe part of the reason why calculus has become so successful is because due to Bayes, there might have been too much criticism against it for it to get off the ground if it weren't for him. So I think that was another great thing he did. But anyway, that completes my bio on Thomas Bayes, a pretty great mathematician from the 18th century. So thank you for watching. Long live math, and I'll see you guys next time. Bye.